If you look at the physical architecture of modern artificial intelligence, it presents an overwhelming sense of scale. But at the center of that vast web of fiber optics and server racks sits a single, absolute orchestrator. Centralized AI models require data to be physically pooled. To train a state-of-the-art system, every parameter, input, and weight must be consolidated under the control of one corporate entity. This chart shows the architecture of distributed AI. It addresses the computational bottleneck by spreading the workload across multiple physical machines. But notice where the authority remains. Execution is separated from governance, leaving the central company node in complete control of the network. Even in edge AI, where inference gets pushed out to your phone or a local server, the model weights and data access policies are still routed through that single administrator. Distributing compute power does not decentralize governance. It leaves a structural single point of failure that compromises data privacy and total network sovereignty. To understand why a truly decentralized architecture is necessary, consider the challenge of building a global predictive analytics model across isolated hospital networks. Raw electronic health records contain highly sensitive variables. This data is the most valuable asset for training medical machine learning models, mapping symptom progressions and treatment outcomes with extreme precision. Strict legal frameworks like HIPAA and the GDPR exist specifically to block the transfer of this information. Pooling raw patient histories into a centralized tech giant server is an architectural and legal impossibility. The engineering objective becomes clear. Design a system where competing hospitals collaboratively train a shared machine learning model without ever exposing patient data or surrendering intellectual property to a third-party mediator. Meeting this objective mandates the complete removal of the central corporate orchestrator. It requires a shift to a purely trustless, decentralized AI architecture. The first step in removing the central server is replacing it with a peer-to-peer distributed ledger. This acts as the foundational layer for tracking the state of the network. A hospital node registers a model using a decentralized identifier and an IPFS cryptographic hash. With no corporate database, standardized ontologies align input and output formats, allowing a Tokyo model to process London's data seamlessly. Because of these standardized rules, the network operates as a permissionless global registry. Any node can query the ledger to find resources without requesting API keys from a gatekeeper. Verifiable decentralized identity and strict ontologies transform a chaotic swarm of peers into a highly legible, discoverable marketplace of AI services. Even with discoverability solved, the core legal constraint remains. Raw medical records cannot leave local servers. The solution relies on decentralized federated learning. The model trains locally inside the hospital's firewall. Only the resulting mathematical gradient updates, the specific parameters adjusted, are broadcast back to the network. Standard federated learning has a known vulnerability. A malicious node can reverse engineer broadcasted gradients to reconstruct patient data, or inject poison data to corrupt the global model. This visualization maps the critical countermeasure, fully homomorphic encryption, or FHE. FHE allows the network to perform mathematical operations directly on ciphertext. The gradient updates interact and aggregate without ever being decrypted into raw numbers. FHE completely decouples machine learning from data exposure. It allows collective intelligence to scale securely across adversarial or highly regulated environments. If the network is entirely trustless, how do we prove a remote hospital actually ran the correct model and didn't simply falsify the output? The system answers this using zero-knowledge machine learning as its verification standard. This circuit illustrates a ZK snark. A node generates a cryptographic proof confirming it executed the exact inference requested. The protocol instantly verifies this math without accessing proprietary weights or patient input. Once validated on-chain, consensus permanently records the verified block. Zero-knowledge machine learning eliminates the need for institutional trust or external corporate auditors. It replaces them with deterministic, cryptographic truth. Maintaining this infrastructure requires immense processing power. The network faces a cold start problem. Independent hardware providers need a reason to spend expensive compute cycles verifying these zero-knowledge proofs. The solution is an embedded incentivization layer. Tokenized smart contracts automatically execute value transfers to hardware nodes the precise moment a cryptographic proof is verified. To protect the system, the protocol relies on a decentralized reputation score. Nodes are financially penalized, their staked tokens slashed if they submit invalid gradients or fail uptime checks. System parameters, fees, and upgrades are managed through decentralized autonomous organizations. These govern via meritocratic voting, weighted by reputation, rather than corporate executive decisions. Crypto-economic incentives and DAO governance generate a self-sustaining feedback loop. The network pays for its own maintenance and enforces its own rules, entirely replacing corporate administration. The completed DEAI matrix achieves global collaborative training with zero data leakage and possesses no central point of failure. Achieving this trustless state requires a severe architectural trade-off. The system is computationally inefficient. This split-screen chart visualizes the discrepancy. On the left is standard centralized compute time. On the right is the massive processing overhead required to generate zero-knowledge proofs for large neural networks and perform homomorphic encryption. The latency spike is exponential. This cryptographic friction stalls the training epoch. Currently, it limits decentralized AI applications to smaller models or asynchronous tasks, where a delay in processing is mathematically acceptable. Decentralized AI is not optimized for speed. It is a strict architectural mandate for environments that require absolute privacy and verifiable trust over rapid execution. The primary barrier preventing mass adoption of decentralized AI is computational, not theoretical. Overcoming this requires abandoning general-purpose processing. A standard CPU cannot efficiently handle the dense mathematical requirements of cryptography at scale. Hardware manufacturers are rapidly developing specific application-specific integrated circuits and specialized GPUs. These units are optimized explicitly for zero-knowledge proof generation and FHE mathematics, designed solely to compress this latency penalty. As physical hardware catches up to the cryptographic theory, the latency gap will close. Decentralized AI will transition from a niche framework for regulated data into the default operating standard for artificial intelligence. The DAI stack provides the final blueprint for an intelligence layer that is inherently secure, transparent, and owned by the network itself, rather than a central orchestrator.